Hi guys, let's take a look at radical bromination of alkanes. Now first off, a little review of reactivity of organic compounds. And we have looked at reactions of alkenes. Okay. The pi bond is a source of reactivity. The electrons are not held tightly. They'll react. Very common reaction of alkenes is electrophilic addition reactions. Okay. So a site of reactivity there. And the alkane portion, typically unreactive. Now we've also looked at molecules with leaving groups. Okay? And depending on substitution, we can have reactivity here of the carbon that the leaving group is bonded to. And we have a different four different mechanisms we looked at: SN1, SN2, E1, or E2. Okay? So two of the common sites of reactivity. Now if we look at just an alkane, where's the reactivity? Now during test one we talked about how we could react these with oxygen, okay, and burn them. A combustion reaction, and each carbon is converted to CO2, and all the H's are used to create water. And we mentioned that this was a radical oxygenation. You can look back at that handout, one of the alkane handouts. We also showed that we could react this with something like bromine, elemental bromine, and get maybe something like this, okay? And this is a radical bromination, and that's what we're going to look at now, all right? Using what seems to be a fairly unreactive substrate, an alkane, can they react? They can't do much. They can do radical reactions. So can you do chemistry with simple alkanes? And the answer is yes. If you take this alkane, react it with elemental bromine, now you need either light or heat or peroxides. All right? This is H nu. This is generic for light energy. Planck's constant times frequency, if you remember that. And we can get a substitution reaction here because, as shown, the H on the tertiary carbon is being replaced or substituted with a bromine. Now it's not an SN2, it's not a SN2 or SN1 substitution. It's a different type of substitution. Now we can complete this line reaction. We're going to generate what? Well, we're going to generate HBr. That's the fate of the H that's replaced and of the other bromine. And this tertiary halide, bromide here, would be our major product. We'll talk about predicting that. And this reaction is usually very regioselective. That is, the bromine here is typically going to end up on the tertiary carbon as opposed to the secondary or one of the primary carbons. Now, we can compare this reaction with elemental bromine to this reaction here. If we had an alkene, we know the alkene will react with bromine to give the dibromide. in an addition reaction of the alkene. And we remember this bromonium ion backside attack, overall transaddition, if that's important for your stereochemistry. All right. And you actually did that reaction in lab when you brominated transstilbene. Okay, so what's the mechanism for this top reaction, which indeed is a radical bromination? The first step is the bromine molecule has to undergo a homolytic cleavage. And this is promoted by either light, heat, or peroxides. Okay? We can shine a light on it. Okay, let's turn the light on it here. All right? A light bulb will provide enough energy, typically. Better if it's a high energy light bulb. Some energy into this bond. I'm going to denote this like this, yeah? Some energy in here. The bond will break, and one electron will go one way and one electron will go the other. Why would they both go to one bromine? They are equal in electronegativity. The electrons are going to split equally. One goes one way, one goes the other. When we move one electron, remember we use a fishhook arrow. And this is going to give a bromine. By the way, there's 3 lone pairs there and there. If we just focus over here, we got 3 lone pairs. But when one electron moves this way, we also now have a single unpaired electron, which we call a radical. A species with a single unpaired electron is called a radical. Now, the other is going to be the exact same. So how about if I just draw 2 here? We're going to get 2 of those. And this would be called homolytic bond cleavage. Because homolytic, because it ends up being the same, 1 electron to each. Now, if we had HBr and something happened here, the electrons would both move to the bromine, and so it would have 2 extra electrons, and that would be a minus charge. Note that the bromine radical is neutral. Okay, it's owning 7 electrons. That's how many it's supposed to own. This would be called heterolytic bond cleavage, because it does not end up the same. You don't get 1 electron on each. You end up with 2 electrons here and none here. Okay, so that's the first step. I'm going to say H nu, light, and I showed the light coming in here. That's not really a mechanistic step. I'm just sort of illustrating that we're shining light on the molecule. All right. Now you can also get homolytic bond cleavage by heating or by adding a peroxide. Now, I'm not going to go into how the peroxide will cause this to happen, but just note that sometimes peroxides are added to promote the homolytic bond cleavage of your halogen. Okay. Now, I'm going to redraw my alkane. Let's draw in the H, which is obviously abstracted. Let's do chemistry with it. The bromine radical, there's 2 of them. Let's just use 1 for now. 1 electron from this bond will come and team up with 1 electron from that atom. And the other electron here will go on to the carbon. Now, why and how is this happening? you know, we don't really have any charges here. I usually just say the bromine radical strips an H out of here. And I can't really tell you much more about the chemistry or really the physics that's going on here. But apparently the electrons in this bond, one of them are attracted to this electron, and they just start wanting to team up. That's very simplistic. But if we just follow our arrow movement here, one electron teams up with that electron, and the other electron stays here, this gives us, if we focus on the organic molecule, we now have a single electron there, and now we have a carbon radical. But what did we form here? Well, we formed our HBr, which we said we would form. Now note, we made a tertiary radical. If you remember, radicals are stabilized the same ways that carbocations are. Thus, tertiary radicals are more stable than secondary, which are more stable than primary. They're stabilized the same way because they're electron poor, just like a carbocation. Now this carbon has no charge. It owns 4 electrons. But it is electron poor because it does not have an octet. So here we have 3 rich friends bonded to this electron poor carbon. The same sort of argument we would make with a tertiary carbocation. And that's the reason for the regioselectivity here, right there. Where you're going to make, you remember we used to ask where we're going to make carbocation? Well, the question here is where we're going to make radical in this alkane. Now, how can we get final product? Well, we do have a bromine radical, a second one. That electron can team up with this electron to make a covalent bond between the carbon and bromine, and that would give us the product. But that's not the mechanism. Because if we did that, how would we then make a second molecule of product? We would then have to have bromine undergo another homolytic bond cleavage promoted by light. But we know something about this reaction and the light. You can actually turn the light off and the reaction will continue. It will sort of propagate on its own. So our mechanism needs to account for that. All right? And thus the mechanistic theory is, and other support for the theory, is instead of this carbon capturing a bromine radical to give you final product, it instead reacts with another molecule of Br2. And one of these electrons teams up with this electron, and the other electron moves on to bromine. And that arrow movement gives a carbon-bromine bond, because the carbon electron teamed up with the bromine electron. Yes, there's 3 lone pairs on all these bromines. Plus, what do we make with this arrow? We made a bromine radical. And we made it without light or heat or any other way. So our mechanism now, if we use bromine, elemental bromine, produces bromine radicals, and we can turn the light off. And now to make another molecular product, this can come over here and repeat the process. We would need to bring in another, of course, another alkane, another molecule of alkane, and another molecule of bromine, create another molecule of product, but we also create a bromine radical, which can then come back over here. Then we bring in another alkane, another bromine molecule of bromine. So we get this continuous cycle. That's called propagation. So we want to show the mechanism that way. To make sure we understand how propagation occurs and takes place. So there's our product. We made HBr, we made here. It's a radical mechanism. All your intermediates, well really this is the only intermediate, well that and that, they're radicals. They're not ions. Okay? So it's not an ionic mechanism. Okay, let's see if we can predict some products. Methyl cyclohexane reacted with elemental bromine and some light. What product do we expect? You can pause the video, show the product. Okay, I'm going to expect a bromine here at the tertiary carbon. And I'm going to also produce HBr as a side product. And there's the product would form by a radical bromination reaction. Regioselective for the tertiary site. Okay, mechanism as above. All right. How about the next one? A bromine. What is that? Well, it's two oxygens. Okay, and each oxygen is bonded to a benzoyl group. That's the structure of this condensed here. A lot of times if you see diethyl ether, well, it's only one oxygen, but a lot of times it will be Et2O. Okay. Now this has parentheses around it because it's more complex. That's an oxygen with two ethyls. This is two oxygens, and then there's two benzoyl groups. This is, first off, if these were H's, that would just be hydrogen peroxide. These are benzoyl groups, and so this is called benzoyl peroxide. You may have heard of that before. In the pharmacy, it's used to treat acne. and a benzoyl peroxide cream, like up to 10%. Basically, just like bromine will undergo homolytic bond cleavage, peroxides will do it as well, and benzoyl peroxide is particularly prone to doing it to create benzoic radicals. But then those radicals can promote the formation of bromine radicals. Let's don't get into the details there, but just note that sometimes radicals let's call this a radical promoter. Okay, your peroxide, the most common is benzoyl peroxide. Whenever you see peroxide, it's going to be an indication that we're doing a radical reaction. Okay, so this is all radical. The question is, where we're going to form a radical at on our substrate, and the answer is at the benzylic site. All right. I'm just going to show a radical that we could form by the mechanism like that. Okay. And that would be a benzylic radical. And just like a carbocation, that's particularly stable, because we can do resonance of radicals. And let's show that. Okay. Now we don't just do a windshield wiper because there's one electron here. We're just going to move. Now I'm going to treat the outer as the pi bond. I'm going to move one electron in here and this electron in there as well, and the other electron out here. And this electron in the pi bond moves here to team up with that electron. I kind of lost it when I drew my arrow there, to make double bond there. And we moved radical here, okay? Then we can take one of these electrons in the pi bond, move them over here, and team up with that one, and move the other one here onto the carbon. And this is how we show resonance of radicals. So we made pi bond here by teaming up one electron from there and one from the pi bond, and we move the other electron from the pi bond here. Nothing there, nothing here. And then we can move one of these here and this one here, and one of these out. There we go. Now if we took this one, moved it in, and one of these in, and moved this one out, we're going to get back to having our radical on the benzylic carbon. Now again, the pi bonds will be moved around in the ring, and so I'm not going to show that additional resonance structure, but we're saying that the radical, the lone electron, is now back on the benzylic carbon. Okay. Now in terms of what we have here in terms of p orbitals, where of course every atom in the ring has a p orbital. One electron in each. Pi bond, pi bond, pi bond. Okay, you can see that if you think about that. Well, the radical also is going to be in a p orbital. Okay. And the carbon with the original radical is sp2 with p orbital, just like if that was a lone pair. If that was a lone pair, we would say it's going to be sp2 and the lone pair would be in a p orbital because it's next to a p orbital. Well, the same thing goes with a single electron. It doesn't have to be a paired or two electrons. A single electron will also want to be in a p orbital. And so you have overlap of 6 but also 7. There's 7 p orbitals overlapping here. Becomes one system. The electrons are really spread out all through there. These end up being 4 fake structures. And so, but the radical is delocalized. It's not just one carbon with a single electron and electron poor. You've got several atoms that are sharing that negative feature. Not a charge. There's no charge here. Instead of having one carbon that's electron deficient, we have semi-electron deficient on several. Okay. In the end, benzylic carbocations are quite stable. Benzylic radicals are quite stable. This is going to then capture a bromine from Br2, just like we did right there, to end up with a bromine on the benzylic carbon. Yes, plus HBr. Okay, typically we're just showing the major organic product. Okay, what is NBS? NBS is an alternative source of bromine radicals. Okay, it is a solid. It is safer than Br2. Okay. Br2 is a liquid, but it's also very volatile. Okay. If you open it up, vapors will come into the air, and it will be likely to be breathed in if you're not careful. All right. NBS is a white solid. You spill it, you just sweep it up with a broom. You spill bromine, you're going to probably have to evacuate the lab. All right? So it's a safer alternative. In NBS, well, first off, the name, succinimide, if that was NH, that would be succinimide. Here we have a bromine on the end, and so it's called N-bromosuccinimide. And with light or heat or peroxides, it will undergo, guess what? I'm just going to do something like that. That would be is one lone pair there, right? And one electron, because there's one lone pair there. It's just a ring. I'm not going to draw it all out. Plus Br radicals. Now it turns out that only the Br radical is going to react with your organic substrate. We won't explain why. Whenever you see NBS, and especially it's going to include something like light or peroxides or heat, you're doing a radical bromination. And the question is, where's the best place to make radical? And it's going to be right here. Same place as it's also the best place to make carbocation. That would be an allylic radical. Okay. And and we can then envision the product being, okay, see, this will capture a bromine from NBS. Think through that, yeah. Okay, up here we made HBr. I'll draw that in, okay. What did we make down here? What was the byproduct here? It's actually, the H ends up with the other radical. You're going to make succinimide, which we drew there, okay. That is organic, but this is your main product coming from the original substrate. Now, there's actually two possible products here due to resonance. If we consider resonance over here, this electron here, this electron here, and this electron out, we can get resonance. Now, in this case, this radical can actually react with the bromine, or in this case, NBS. Let's just draw that like that. And one electron here, one electron here. And we can get product that looks like that as well. Now the question may become, well, why did we react with another resonance structure here, but here we had multiple resonance structures? See, with the benzene ring, you're never going to react to give a product in which the benzene ring is no longer aromatic. So if this captured a radical, a bromine radical, the product would look like that there. There is an H there. Thus now that's sp3, okay, no p orbital. This ring is not aromatic. Thus, this product is a lot higher in energy than this product, because it is aromatic. Thus, the transition state for this reaction, capturing bromine here, is going to be higher than the transition state leading to that. Again, you're not going to destroy your aromaticity usually when you're doing benzene reactions. But down here, we can consider the other resonance structure because the two products are both just alkenes. I'm sorry, here's the two products. Now, and actually, we could say, well, which one's going to be major? And this would actually be your major product, and this would be actually minor there. And so that's because of alkene substitution. That's a disubstituted alkene, that's a monosubstituted alkene. So this reaction, we can envision getting two products, but this one here actually being major. Need to be able to show both of them though. Okay, why can't we use bromine in the last example above? Why did we use NBS? And actually you have to, because if you tried to use bromine, the alkene would react instead, just like here. Alkenes react with bromine very fast. No extra energy needed. So NBS, not only being a safer alternative, it actually will not react with alkenes and will allow you to only do the radical chemistry. You won't get the addition of bromine to the alkene to give the addition product. Now with a regular benzene ring that's simple and not activated, bromine will not react with a benzene ring. You'll learn more about that in Organic 2. Now bromine can react with benzene rings, but not in this particular case as shown. So you will need to learn more about that in Organic 2. But we do know now that an alkene will react with bromine, and so here we need to use the alternative NBS. Okay, why is the ability to put a bromine on an alkane so important? Well, look what we now have. We now have a leaving group, a traditional leaving group. Now we can do lots of reactions, substitution, elimination, plus other reactions we've not yet covered, such as Grignard reactions, which you'll see in Organic 2. All right? I mean, we can now react this, and I want you to pause the video here for some review. What if we react this with KOH? Okay, what would be the product? Please pause. Okay, product would be, of course, that alkene. And we're doing an E2 elimination. I showed Zaitsev product. All right. What if we then came in here with BH3 followed by hydrogen peroxide and sodium hydroxide? Please pause the video. Okay. Well, if you remember from test 2, this is a hydration of the alkene, Anti-Mckarnikov. This would give this alcohol. All right. Well, what if we took this alcohol and reacted it with, let's see, sodium first, and then came in here with ethyl iodide? Please pause the video. Okay. Well, that would give that ether, Williamson ether synthesis. You know, we can do all types of things. What if we reacted this with HBr? Maybe we're looking to get that product there, which is actually an isomer of the original. Yeah? Basically, once you get the leaving group on there, now you can get, and if you get to an alkene through an elimination reaction, now you can do any chemistry you want. And so we went from a very unreactive, very simple hydrocarbon, which maybe came from petroleum, which originally comes from natural products, that we can start building bigger and bigger molecules and maybe some drug that cures cancer. So the radical halogenation gets you started from simple alkanes. Why only bromine typically? Well, we didn't look at it, but the thermodynamics of these reactions, bromine is sort of the right sweet spot between not being overly exothermic, but also not being endothermic. If you try to do these reactions with chlorine, they won't be as selective, as regioselective, because the chlorine radical is much more reactive. The CCl bond is much stronger, and thus your reactions are going to be more exothermic, and they're going to be faster. And being faster, you're going to lose selectivity. It'd be like a bull running through a china shop. It's just going to knock everything down. It's going to react everywhere. Bromine is slow enough mild enough that you can achieve regioselectivity that we talked about. On the other hand, iodine, trying to iodinate an alkane with iodine is actually an endothermic reaction, and that's very difficult. And those reactions actually tend to go in reverse. We may mention that later. Here's an example of a radical bromination in making the cancer drug anastrozole, here, number 2. If you're looking going from 21 to 22, step back a bit, they're reacting this 21 with benzoyl peroxide and NBS. They're also using carbon tetrachloride as solvent. All right. Got to be careful about what solvent you use for radical reactions. You don't want a CH in your solvent. And we see that they did a radical bromination at the benzylic carbon here. Then they came in with this nitrogen anion, 2 lone pairs, and they did the old boop, SN2 to get the nitrogen bonded there now. So the radical reaction got a leaving group on that benzylic carbon. Up here they started with this dibenzylic dibromide, potassium cyanide, SN2, double SN2. Then here they put methyl groups on. The sodium hydride acts as a base and it forms anion here. All right, and they do this 4 times, and then they react that with methyl iodide. I'm going to draw the iodine like this, and so these electrons attack carbon, kick that off, and you end up with a carbon bonded to the methyl. But again, they repeat it 2 times on each carbon to get 4 methyl groups on there, and so that's also SN2. C alkylation. All right. So really several SN2 reactions here along with a benzylic radical bromination. Miscellaneous topic. Why are so many halogenated alkanes harmful to the ozone layer? Okay. A lot of your refrigerants are small halogenated alkanes, but they're harmful for the ozone layer, and so they're being phased out, no longer used. Because with light will promote bond cleavage. And what will happen here is the carbon-chlorine bond will undergo homolytic bond cleavage, and that will produce that radical plus the chlorine radical. Now I chose to break the weaker bond. The carbon-chlorine bond is weaker than the carbon-fluorine bond. But these radicals will react with O3. I'm not going to show any chemistry, but they'll react with O3 and consume it or destroy it. Okay, so that's freon gas. Used to be used as a refrigerant, not used anymore. Methyl bromide is used as a fumigant, but the same thing. We can get radicals. Chloroform is a common solvent in the lab. Same thing though, we can get radicals from these. So halogenated alkanes tend to form radicals with sunlight. Okay, you get up in the atmosphere, there's lots of sunlight up there, and it'll promote forming radicals, and they'll react with the ozone. going to let you look at these on your own. Okay, interesting mechanism here. I mentioned iodide compounds. They tend to be unstable. Okay, and that's described here. But I want to move to the back page. Anti-Mckarnikov addition of HBr to alkenes. This is actually a reaction we skipped during test 2. Shown here, but let me introduce it. First off, remember we hydrated alkenes. We did a Markovnikov hydration using either aqueous acid or oxymercuration followed by reduction. Okay, and both of these gave the alcohol with the oxygen bonded to the site where you would predict carbocation. Carbocation on left or right? Left. Water adds, okay, lose proton, get this product. Oxymercuration gives the same product. We call that a Markovnikov hydration. On the other hand, with the OH bonded to the other carbon, this is not like oxygen bonded to carbocation. It's the reverse. We call this the Anti-Mckarnikov product or hydration product. And we can do this using borane, BH3, followed by the magic step, you remember, oxidation. It's actually the same thing I showed over here. Okay, so it's a good chance to review our alkene chemistry. Now with HBr, we can do a simple Markovnikov hydrobromination. Carbocation on tertiary, bromide attacks carbocation. There you go. The one thing we never asked or answered was, can you do an anti-Mckarnikov hydrobromination? Can you add HBr to an alkene but get the reverse regiochemistry and get the regioisomer? And their answer is actually yes. And you can do this by reacting with HBr, but just including a peroxide. And if you include the peroxide, you get the reverse regiochemistry. Now you may remember, some of you actually asked about it, that alkene puzzle actually showed this reaction there, and you might look back at the alkene puzzle. All right. Mechanism for this reaction. Well, the bromine radical is the initial electrophile instead of H+. Turns out if you take HBr with peroxides, it will undergo a homolytic bond cleavage. And you'll get H radical plus Br radical. You see, guys, I really don't like this mechanism because it's so confusing with the other one over here. There's so many questions that will come up because the other one also had bromine radicals. But here, with the alkene will react with the bromine radical. And the question then becomes, well, why did we not react over here with this alkene with the bromine radical? Yeah, that's a great question. One electron teams up here, and the other electron goes here. And this would give bromine here. And we made a tertiary radical. All right, which is where we would have predicted, right? Well, just like before, to give us propagation, instead of this quenching with the H radical, let's react with, take one electron, H nucleus, carbon teams up with H, and we create this plus Br radical. And that's for propagation. And now the tertiary carbon has an H there. All right. But I hate this mechanism, particularly when comparing it to the other mechanism. And why, for example, did the bromine radical not take an H and make a allylic cation here? Probably has to do with thermodynamics and equilibrium, and ultimately we have to think about some memorization here. And here's the thing. If you have an alkene and you're reacting with HBr, if you see peroxides thrown in, okay, this is going to be an addition reaction. It's an addition of HBr with reverse regiochemistry. That is anti or non-Markovnikov. All right. Where if you react with bromine, elemental bromine and peroxides, like benzoyl peroxide or light or something, this is a well, the problem is you got bromine. That's going to do an addition reaction to the alkene. Let's change this to NBS. See, NBS never reacts with alkenes. At least not in this class. That's going to give radical. This will avoid the alkene. Okay. Where if you take this with bromine and peroxides or something, well, it's going to give you the dibromide, and the peroxides ain't going to do anything because bromine is going to react with the pi bond so quickly it's just going to be a good old addition of Br2. Okay, predict the products. I'll let you do those on your own. Okay. Please look back at the alkene puzzle. I think it's posted on the team's website. Please take a look at a couple of these miscellaneous topics. You know, particularly if you're interested in some interesting chemistry and applications of the chemistry the fundamental chemistry we talked about here on the first page. All right. Okay, guys, I'm going to end it there. See what type of questions come up on these radical reactions.